In this module, we're going to discuss the divergence of vector fields. So before we proceed with the discussion on divergence, let's have a short example. So here we have an electric flux density that is due to a positive point charge. So the positive point charge is located on the origin, and it is defined by this equation. So this flux density is shown graphically by the lines represented by the red arrows. So the farther you are from the origin, the longer are the arrows, indicating that the flux density is getting stronger as you go away from the origin. So this example is not typical of the actual flux density due to a point charge, because in reality, the farther you go from, or the farther you are from the point charge, the weaker is the flux density. So we want to know if a net flux is leaving the area S, where the area S here is the shaded area. So here we have three lines entering the area. So we have here a line, this line here, and this line here, and also the same lines that is leaving the area. So this line, so it's a bit longer because it is farther from the origin, and this line as well. So we also would like to get the line that is only perpendicular to the surface of the area. So let's say this is this line here that is perpendicular. So this line and these lines. So here we have about 3 units that is entering. So into the area we have 3 units, and the units leaving the area is, well, this is the lines here, here, and here. So this is 3 units, 3 units, 3 units. So there are 9 units that are coming out of the area. So we have a net that is going out of the area S of 6 units. Okay, so here we have shown that a net flux is actually leaving the area, and because of that, we can say that this point here, the center of the area, is said to have is said to be diverging with a roughly numerical figure of 6 units, which is actually the average that we got for the area. Okay, let's have a more formal definition of divergence of a vector field. So the divergence is really a measure of how the vector behaves on a particular point, whether the vector field is expanding at that point or if it's shrinking. But let's make a more formal definition of that. So let's say I have here a volume, small volume, and let's say flux is entering that volume, and it is also leaving that volume. So the net flux that leaves the volume would be, well, basically the flux leaving minus the flux entering, divided by the volume to which those flux is entering and leaving. and that would somehow give us an idea on the divergence of the field at this point here. But mathematically, it is given by this one, which is given as the surface integral of the vector field dotted with a incremental surface. So for example, we have here a vector, let's say a vector here, and we have here a small surface, ds. So we take the dot product of that and we add all of those uh, dot products over the entire surface. And then we divide it by this volume here, and we let that volume shrink into an infinitesimal volume, and we take that limit. What we're going to get is the actual divergence of the vector field at that point here. Doing that will actually show that the divergence of the vector field at that point is actually this operation. So we assume the del operator to be a vector, and we do a dot product of the vector field at that point, or the vector at that point, and that will give us the actual, a more accurate picture of the divergence of the vector field at that specified point. So that is the formal definition of divergence. Uh, so given a vector field A, the divergence is simply the del operator dot uh, dotted on the vector field. So we assume the operator to be a vector. And for Cartesian coordinates, that will give us this expression. For cylindrical coordinates, that will give us this expression. And this is for the spherical coordinate system. Here are more pictures about divergence. So the one on the left is positive divergence because the field is expanding around point P. The one in the middle is a negative divergence because the field tends to converge to point P. And the one on the right is has a zero divergence because the amount of field that enters the point P and the field that leaves point P are the same. Here we have another picture of the actual vector fields of a point charge. So as you can see, the at the middle, so this is colored blue here. These are the values of the electric field. The red ones are this one, so it's a bit higher. It's much higher actually. And here we have the values here. So this one has a positive divergence. Here we have the fields produced by 2-point charges. So here we can say that the field here is diverging. Here where the fields are in parallel, we can say that it is zero because equal amounts is entering, or the fields coming from the left, the amount of fields coming from the left is the same fields going out on the right side. Here we can say that the field here is diverging or converging, and therefore it has a negative divergence. Here is a field of the coax cable. So here it is diverging. It has a positive divergence. Here are some more statements about divergence. So it is a measure of how much the field diverges or emanates from that point. We can also view divergence in um, from the standpoint of a source of a field. So we can say that let's say a point is producing a field. So we could say that it is the source of the field. So we view that as a positive divergence. But if it actually absorbs the field, we call it a sink. So therefore, divergence there is negative. It is also the measure of the strength of the source. If uh, field is a source is the source uh, if the field is coming out from out of that source. We also have identities about divergence. So, for example, the divergence of the sum of two vector fields is the sum of their individual divergences. Also, if we get the divergence of a vector field that is multiplied by a scalar, what we get is this expression. Let us have some examples to illustrate divergence. Here we have vector fields in different coordinate systems, and we're being asked for their divergence at specified points. So for letter A, it is expressed in the Cartesian coordinate system. So this is the formula for divergence. So the first term there is simply the partial derivative of the component of the vector field along the x-axis plus the partial derivative with respect to y of the y component and plus the partial derivative of the z component of the vector field. So for the first term, we have the partial derivative of yz, and that should be a 0 because yz has to be treated as a constant. For the second term, we will have 4x there, and for the third term, it is also 0 because y is treated as a constant. So that will give us an answer that is equal to 4x. And substituting for the value of x, that will give us a value of 4. So the divergence of the vector field B at this point is equals to 4. It is positive 4. So therefore, this is a positive divergence. And take note that divergence of a vector field always yields a scalar quantity. For letter B, the vector field is expressed in cylindrical coordinates, so we use this formula here. And for the first term, uh, QR here is this one, and we first substitute it there and combine it with the R here. So we will get here actually R squared Z sine phi, and we get the partial derivative with respect to R that will give us 2R Z sine phi, which the R cancels in here, so therefore that will give us 2Z sine phi. Here, this is treated as a constant, so R here and R there will cancel, and the derivative of the cosine phi is negative sine phi, so therefore we will get this term. And substituting the points, we will get a negative divergence equals to -1. So in this example, the vector field is given in spherical coordinates. Take note, we don't have a component along the theta axis. So this is the formula. So first we note that this term here is this one. So we substitute it here. And first we combine it with r squared here and we get an r cubed. So then we get the partial derivative with respect to r, and that will give us 2 times 3, 6 r squared, which the r squared cancels in here, and that will give us this one. Here, square root of r is treated as constant, so the partial derivative with respect to phi will be 0, and that should give us this result. Substituting the coordinates, that should give us a positive divergence. So that's it for this video. On the next video, we're going to discuss about the curl of the vector field.